Estimating area with Riemann sums. We're going to be looking at area under a curve, and under is a little bit of a misnomer here, but it's commonly used when we talk about the area. And when we say under a curve, we really mean the area between the curve and the x-axis. So not literally underneath the curve as in below, but you see three different illustrations of area under a curve here. As long as you're trapping the area between the curve and the x-axis, that is what we are referencing here. And in some cases, the curve crosses the x-axis, and when that happens, you kind of swap the idea between what's below the x-axis and above, below the curve and above the x-axis, and below the x-axis and above the curve. Don't really have to worry about those in great detail, just wanted you to understand visually what we are doing. And we are going to use a method called Riemann sums, which is really glorified geometry, where you are going to divide the area we are interested in into rectangles of equal length bases, if you can. Sometimes the way the problem is presented does not allow rectangles with equal length bases, but you will have rectangles of bases, and the height of the rectangle is going to be determined by the function. And so let's look at some illustrations of how that would work. There are several different types of using rectangles and Riemann sums to approximate area. We are going to look at three in this video. One of them is a right Riemann sum, where you are estimating the area, and here I'm going from A to B. You can see my green A and green B down here, and I want the area under f of x from A to B. And I have divided this one up into 1, 2, 3, 4, 5 subdivisions, and the bottoms of my rectangles, the bases are equal length, and I am bringing my rectangles up until the right corner is hitting the curve. And so this is an illustration of a right-handed or a right endpoint Riemann sum. And you'll notice that it's not going to account for everything. You're going to have a little bit of error when you are using Riemann sums. Here we have some under approximation. These rectangles are not filling up the whole area, whereas this rectangle, the very first one, actually has a little bit of an overestimate involved, and that's going to happen with Riemann sums. Don't let that bug you. So if there is a right-handed Riemann sum, then there is also a left-handed Riemann sum, where again I have my subdivisions. I have 5 different rectangles, and they are evenly spaced out from A to B, and I bring each rectangle up until the left side of the rectangle hits the curve. So we had a right endpoint, a left endpoint, and again you'll see that there's a little bit of error in these. They're not exact. And then the third one we're going to look at is a midpoint Riemann sum, where again you divide the region up into equal length bases, and we have 5 rectangles once again. And this time I brought my rectangles up until the middle of each rectangle is hitting the curve. And if you look at these rectangles, a midpoint, if you're worried about accuracy and getting as close as possible to the actual area, midpoints do a decent job of that. There are still better methods, but you'll notice with each one of these rectangles, you have, as I've drawn this one, we have a little bit of overestimate and then a little bit of underestimate with that rectangle. If you look over here, I have a little bit of underestimate and a little bit of overestimate. So when it comes to accuracy, midpoints are the way to go, but you will be asked to do left endpoints and right endpoints as well. And before we look at some hardcore examples, let's go back to my left endpoint illustration here, and let's talk about how we will use this to get the actual area. And of course, you should know that the area of a rectangle is base times height. And in these Riemann sum, the base is your change in x. However far you're going from one x to the other x is the base. So base is your change in x. And the height is determined by the function values, the f of x. However, whatever y coordinate you achieve is your height. So the height is the function values. And if you want to get the delta x, if you're doing evenly spaced intervals, so right here I have 1, 2, 3, 4, 5 rectangles, and I'm going from A to B. If you want your delta x, you'll do the length of the whole interval divided by the number of subdivisions. And so right here I can physically count 5 subdivisions. So each delta x would be b minus a over 5. And if there's n subdivisions, if we don't know how many there are, then the delta x will be b minus a over n. And that's a little bit more of a generic way of finding the delta x. And then to find the actual area, each rectangle would have a base of delta x and a height. My first rectangle is my y coordinate at that very first x value, which I'm going to call x sub 0. So delta x times f of x sub 0. My next one is delta x times f of x sub 1. And I'm going to pause the recording and finish all the rest of these and come back and show you what we can do with this expression. Okay, and there you can see my final expression. I have 1, 2, 3, 4, 5 rectangles and 1, 2, 3, 4, 5 areas represented with delta x and the function value at the different x coordinates. Notice my last rectangle does have a height at x sub 4, not x sub 5, so we stop at x4. And if you have evenly spaced subintervals where your bases are all the same, you could then factor out the delta x to give you a final area of delta x times f of x sub 0 plus f of x sub 1 all the way to f of x sub 4. So if you have evenly spaced subintervals, then you can make it a little bit easier on yourself by factoring out that delta x. So let's go on and look at 3 specific examples, one of each type. And so this one, we're looking at the function y equals x squared over 2 plus 2, and we're going from 0 to 4. I want a right endpoint Riemann sum with 4 equal subdivisions, and we can designate that as R sub n. R sub 4 means right Riemann sum with 4 subdivisions. And we do want subdivisions of equal length. And this one's not too hard. If you're going from 0 to 4 with 4 subdivisions, each rectangle will have a change in x of 1. But if you want to kill it dead and use our little formula, your delta x is b minus a divided by the number of subdivisions. And in this case, that would be 4 minus 0 divided by 4. And we get a delta x of 1. And so each of these rectangles has a base of 1, obviously. And now I need to find the heights of those rectangles, and my heights are determined by the function values at the right end of each rectangle. So my first rectangle, or my area, my right-handed Riemann sum with 4 subdivisions, I have a rectangle of base 1, and then the height is your function value at the right end point of the interval. So my first one is going to be f of 1 plus, and then base of 1 times f of 2 plus base of 1 times f of 3. And then my last rectangle has a base of 1 and a height of the function's value at the x-coordinate of 4. And this looks really silly because I wrote 1 times all of my heights, and I'm even going to be silly again. I'm going to factor out the 1 because my delta x is the same. F of 1 plus f of 2 plus f of 3 plus f of 4. And now I have set up my Riemann sum, and here you should be able to do this without a calculator, but I'm going to cheat and throw this in a calculator. Everything from here on out is arithmetic, and I'm not going to bang that drum too hard right now. So I'm going to pause recording and punch this in, and we will look at the next couple of examples. And when you punch that in, you get 61 over 2 or 30.5 if you want to go the decimal route. So let's look at a midpoint Riemann sum. And this time I chose not to include the graph because you really don't need to see the graph when you're breaking up your Riemann sums. The main thing you're interested in is how your x-axis is divided up and what numbers on the x-axis you will use to get the heights. So here I needed to see what my delta x's were, and I needed to know what x's am I plugging in. This was a right endpoint sum, so I'm going to circle the right side of each interval. That's how you're going to determine how to set up your Riemann sum. Having an accurate graph really isn't necessary. So on this one, I'm being really lazy. All I have is my x-axis. We're looking at this function from 0 to 6, and I want to do 3 subdivisions of equal length. So first thing I'm going to do is determine what is my delta x. That'll be 6 minus 0 divided by 3, or 2. So each of my rectangles is going to span a length of 2. So I'm just going to draw some generic rectangles here. And this is not at all what they would look like if I were to actually draw the function, but I'm just putting something in here to have the visual. And I can look at these rectangles and I can tell that the base of each rectangle is 2. And I'm going to use the middle of each interval because this is a midpoint Riemann sum. I'm going to use the middle of each interval to determine the height of my functions. And so my midpoint with 3 subdivisions, the rectangles have a base of 2, and my first rectangle would be the function's value at 1 is going to be the height. My next rectangle, a base of 2, and the function value at 3 is going to be the height. Wow, that was a horrible vertical line. And then my last one, a base of 2 again, and the function's value at 5 will be the height of my last rectangle. And then we can factor out the 2, throw this in a calculator to get your final answer for the midpoint Riemann sum. And I plug that in a calculator to get 306 for our midpoint approximation for this function. And then the third kind we're going to look at is a left endpoint. And this time, instead of giving you an explicit function, I'm giving you a table of values for some continuous function. And you are instructed to use 4 intervals indicated by the table. And a long time ago, I mentioned that sometimes you may not be able, you may not have enough information to find equal length bases. And this is how this can happen. You could be given a table of values where you're just kind of at the mercy of whatever they give you. So here we're going from 0 to 10, and I want you to use 4 intervals indicated by the table, which means we have to go from 0 to 3, from 3 to 5, from 5 to 9, and from 9 to 10. If you try to use equal spaced intervals, you're going to have a hard time because the delta x would be 10 minus 0 over 4, which ends up being 2.5, which means I would need to know the function's values at, if I'm using the left endpoint, right? Where's the instruction? Left endpoint, there. If I'm using left endpoint, I'll need my left endpoint of 0. My next endpoint would happen at 2.5, and that's not in the table, and you're not allowed to create your own information to solve the problem. So you're at the mercy of whatever the table gives you. So I'm looking here, and the delta x is inconsistent this time. We don't have the same delta x. My first delta x, I go up by 3, then I go up by 2, then from 5 to 9, I'm going up by 4, then from 9 to 10, I'm going up by 1. And remember, we are using the left endpoint, the left side, to get the heights of the rectangles. So my left endpoint with 4 subdivisions is going to be, the first rectangle has a base of 3, and then the left endpoint is at x equals 0. Plus, and then my next rectangle has a base of 2. A left endpoint, if I'm going from 3 to 5, the left side is at 3. Then 4, and the left side of this interval, I'm going from 5 to 9, left side is 5. And then my last rectangle, a base of 1, and the left side is 9. And we can pull these values from the table. F of 0 is 2. Plus 2, f of 3 is 6. F of 5 is 4. 4. And f of 9 is 7. And we just do the arithmetic. That's 6 plus 12 plus 16 plus 7. What's that? 18, 34, 41 is what I'm getting. Hopefully I did that correctly. I just slapped that together very quickly in my head. I think I'm right. 18 and 16 is 34, plus 7 is 41. Yeah, I like that. So there we go. And there's some Riemann sum examples for you. Hopefully that makes a little bit of sense.